Hey everyone, this is Dr. Walker. This is v009C, Graphical Interpretation of Acceleration. It's going to be very similar to the previous video where we found velocity from a position versus time graph. In this video, we're going to find acceleration from a velocity time graph. So the idea is the same. When you have a velocity time graph, so velocity on the y-axis and time on the x-axis, and you have a line, right? So in this case, the line shows that the velocity increased from 4 to 12 meters per second, and it took 10 seconds to do so. So the slope of this line is going to give the average acceleration. As you can see from this line, you have a rise, delta v, and you have a run, delta t, and we know that average acceleration equals delta v over delta t. When we have a straight line in a velocity time graph, then we have a constant acceleration because we only have one slope, so only one acceleration. The acceleration is not changing. Let's look at this your turn. When is the object slowing down? So you want to really think about this one. Pause the video. It's showing a line that has a negative slope. We know that since slope is acceleration, that this means that this is a negative velocity. Sorry, negative acceleration. Slope is acceleration. So what did you pick? You may have been tempted to pick choice A from 0 to 1.5 seconds, which is the whole line, because you may be thinking, oh, negative acceleration, slowing down for the entire time. But that is not correct. So this reminds us of the moving man. Negative acceleration does not necessarily mean slowing down. Sometimes it does, but sometimes it doesn't. Only about half the time does a negative acceleration means slowing down. So remember that you have to figure out if you're slowing down, you have to look at the acceleration and the velocity. Remember, when velocity and acceleration are going the same direction, that means that you're speeding up. But when velocity and acceleration are going in opposite directions, that means that you're slowing down. So these cases here mean slowing down. So we do have a negative acceleration here, but that means we need a positive velocity. So only in this time interval, from 0 to 0.5 seconds, is when we have a positive velocity and a negative acceleration. So that is when we're slowing down. Another way to think about it is look at what the velocity is doing. It's going from 3 meters per second down to 0 meters per second, which is stopped. So you're slowing down if you're going from 3 to 0. But in the rest of the graph over here, you're going from 0 meters per second to -6. A negative velocity, remember what that means? That just means moving to the left, right? This means moving to the right. So for this part of the graph down here, what's actually happening is that you are speeding up to the left because you have a negative velocity and a negative acceleration. So in this graph right here, you are slowing down. Are you going left or right? We have a positive velocity, which means we are going to the right. Slowing down to the right. So I encourage you to write in the comments and tell me what is happening in region 1, which, let's say that we have a line going this way. And I want you to tell me what is happening in region 1 and in region 2 if we have a line that has a positive slope. Feel free to put your answer in the comments so that we can have a discussion. So let's keep on going with our velocity time graphs. If we have a curve, then that means our acceleration is not constant, because the slope at any point, the slope of the line tangent to any point, is always changing. So a curved line indicates a non-constant acceleration, but we can still find the average acceleration between 2 points by finding the slope of the line connecting those 2 points. So this blue line right here, if we found the slope of this line, that will give us the average acceleration between points P and Q. As we can expect, because acceleration is rise over run, change in V over change in T. The last thing we want to look at for this video is instantaneous acceleration. Just like we looked at instantaneous velocity, which was the slope of a line tangent to a position time graph, well, the acceleration is a slope of the line tangent to the velocity time graph. So in this picture here, we know that the slope of this line from A to B gives us the average velocity. But if we have this green line over here, which is tangent to point B over here, then that gives us the slope of this line, right, of this green line, gives us the instantaneous acceleration. And we usually just write A for instantaneous acceleration because average acceleration has the little bar over it. So we can define instantaneous acceleration very similarly to instantaneous velocity. It's going to be defined as the limit as the time interval approaches 0 of delta V over delta T, which means dV over dt. We can also write this in terms of position because we know that this is equal to the derivative of V, and V is dx dt. So we can also write this as a second derivative of the position. So whatever is more useful to you, if you're given the velocity, you can differentiate it to get acceleration, but if you're given the position, you can differentiate it twice to get the acceleration. In the next video, we'll do some examples to practice these new concepts.